Hi, everyone. Today we're going to be learning about our section 9.6, which is graphing quadratic functions using properties. Our five objectives are the following. We'll be able to recognize the graph of a quadratic function. Think the highest degree is 2. We'll be able to find both our axis of symmetry and our vertex of our parabola, which is just a synonym for our quadratic function. We'll also be able to find our intercepts, both our x and our y intercepts. And then we'll be able to learn how to graph quadratic functions using these properties from 1, 2, and 3. Finally, we'll be able to look at our quadratic function, whether it is our U-shaped and we have a positive a value, or it's our mountain and we have a negative a value, in order to determine whether we have a maximum, negative a value, or a minimum, which is a positive a value. Okay, so let's get into it. Our second page is just notes and our formal definition of a quadratic function, where we're looking at our variables a, b, and c. And as long as a is not equal to 0, we'll have that second degree in our function. And our general form is in the format of ax squared plus bx plus c. So if we look at our famous quadratic function, which is just f of x is equal to our x squared, then we are stemming from our origin, and our a value is disguised as 1 here, right? We have our 1x squared, but then both of our b and our c values are 0 because it's really just plus 0x plus 0. So a is equal to 1, b equals 0, and our c is equal to 0. On that right-hand side, we just have our table of values. If you plug in -3 into our function x squared, we'll spit out 9. So a point -3 comma 9 is represented on our graph here if we were to extend our parabola. Now let's look at our first example for this lesson. Instead of, like on the previous page, we had our famous f of x is equal to x squared function, again, having that vertex be at our origin, which is 0, 0. Notice we now have a transformation that's taking place. We're looking at x squared minus 1. And more specifically, this is a vertical shift down 1 unit. And I'll actually bring in a graph onto this slide so that we can really visually see this shift or the shift taking place. So give me a second. All right, so I just brought in our graph and I labeled it with our scale going up by 1 unit each time. Okay, our original x squared graph, remember from the previous page, stems at our vertex being 0. And then if we plugged in 1 for x, 1 squared is y, or 1 squared is 1, which is our y value. So we have 1, 1. If we plugged in -1, we would have -1, 1. If we plugged in 2, 2 squared is 4, so 2 comma 4. Again, if we plugged in -2, we would also get 4. If we plugged in 3, we would get 9. If we plugged in -3, we would also get 9. So again, this is our x squared graph, right? So again, this is our function f of x is equal to x squared. And now let's look at our blue function. What is happening? We are shifting this entire quadratic down 1 unit. So there are a few ways you can go about this. You can create your own separate table and choose values, or you can just look at all of these points that we just plotted and just shift it down 1 unit. I personally think that's way easier. And down 1 unit, down 1 unit. So now we're looking at the following. Here we have it. F of x is equal to x squared minus 1. I'll create the table off to the side to just show you that our x values stayed the same, but our y values are the values that have changed. So we had 0. I'm going to put in 0 here, and then I'll put in -1, -2, -3, and then I'll put in +1, +2, +3. If we plug in -3, square it, we get +9, but now we're subtracting 1 from +9, so we're looking at +8. We plug in -2, we get +4, -1, +3. We plug in -1, we get +1, -1 is 0. We plug in 0, -1, we have -1. And then we have 1, square it, -1, 0, 2, square it, -1, 3, 3, square it, -1, 8. Okay. And then we're done. So the comparison between this table and the table on the previous page is our y values is just one more than we have here. Our coordinate points are -3, 8, and then so on and so forth. Right? Again, feel free to pause whenever you feel like you just need to take in the information, or feel free to rewind if you want to watch it over again, if I'm going too fast. So this is a notes page, really emphasizing on when our parabola is upright or upside down. The biggest thing that you want to look at here is your A value. If your A is positive, so if your A value is greater than 0, then it's going to be right side up. It's going to fan upwards. Very common test question, even final exam question. If your A value is negative, if it's less than 0, then it is upside down. It is going to fan downward. Right? And this is just the formal way of them identifying what I just put off to the side here. So now knowing this, let's utilize that new knowledge in these two examples. We want to figure out which parabola fans upward or downward. Maybe they both fan up, maybe they both fan down, or maybe one fans up and one fans down. So in part A, again, our key is just really identifying what our A value is. And we can do that in part B as well. Our A value in part B is just a +6. And you can make that note. You can make, for part A, it's negative. aka our a is less than 0. In our part B, it's positive, aka otherwise known as our a is greater than 0. So in our part A, if it's negative, what's happening? We have an upside down parabola, so it fans downward. Whereas when our A is positive, we have an upside right or right side up parabola, which means we have it fanning upwards. And then we're done. Another slide of notes. This is just formally defining our axis of symmetry and determining how to find our vertex of our parabola, aka our quadratic function. Our axis of symmetry is in the wording, right? It's this invisible axis that cuts our parabola in half, forming that line of symmetry. If we were to fold over this purple dashed line, the parabola itself would overlap onto itself. And why is it so important in finding that axis of symmetry? Well, once we have our axis of symmetry, right, it's some vertical line, which means x is equal to some number. We're just going to label it as AOS, axis of symmetry. And more specifically, we can identify this using our b and a values in our general equation of our quadratic. So in our whole ax squared plus bx plus c, our axis of symmetry is just negative b over 2a. But why is this so important? Once again, it's so important because once we know what this vertical line is, what our x-coordinate point is, we can plug in that x-coordinate point in order to determine what our vertex. That x-coordinate point is really also known as our k-value in our vertex. And if you have your k-value, you just plug it into the function in order to get your h value. H comma k is your vertex. So now knowing this information, let's apply it to our example 3, where we're given this function, 3x squared minus 6x plus 2, and we want to A, find the axis of symmetry, and then B, find the vertex. So again, our axis of symmetry, negative b over 2a. Our a, b, and c values based off of what we're given in the problem are 3, -6, and 2, respectively. I'll highlight it to help you guys out a little bit more. And again, axis of symmetry is our green divided by 2 times our blue. Let's now plug in these values and we get negative in parentheses -6 all over 2 times 3. Negative times -6 is just +6. 2 times 3 is +6. And 6 divided by 6 is 1. So once again, our h value, I think I said it was k on the other side. It's not our k. I made a mistake. This should be h, right? It's our x coordinate point. We're finding our k. So our h value is 1 here. And now that we have our h value, we can go ahead and plug this into our function to evaluate what our y value is. First, wherever you see an x, put in parentheses, and then fill those parentheses with that h value. And now solve. 1 squared is 1 times 3 is 3. 6 times 1 is 6 plus 2. -3 plus 2 is -1. So our k value, which we'll make purple, is simply -1. Which means our vertex which is our h comma k, is just 1 comma -1. And once again, I'll color code so you guys can really, really see where all these numbers are fitting in. And we're done. Oops. Now we weren't asked to graph it, but if we did, negative or 1 comma -1, it's right over here. Our a value is positive, so it's fanning upwards. And then our y-intercept is when x equals 0, so it's just 0 comma 2. Our axis of symmetry is that x is equal to 1. Which means if our y-intercept is 0 comma 2, we reflect over that axis of symmetry, and 2 comma 2 is also a point. And then if you were just asked to sketch it, 3 points would suffice. It's bad when I free draw these parabolas. But this is what our function 3x squared minus 6x plus 2 looks like. Anytime you are graphing, whether it's a linear function or a quadratic or even a cubic function in this course, you need to make sure you properly label your axes. You have a proper scale, your x and y axis. That's what properly labeling your axes are, or what that means. And then once you put in your graph, you want to name your graph properly too. Sometimes they'll ask you to name certain points, whether it's the vertex or whether it's the y-intercept. Just draw an arrow and type in y-intercept and then put the coordinate point, 0 comma 2. Same with vertex. Vertex, which is 1 comma -1, and then you're done. Okay. Do not forget to do those. Those are really easy points to get and also really easy points to lose on assessments. Okay, so we have a notes page, and then we will probably do another example. So on this page, this is just being able to find your intercepts, and I very vaguely spoke about it on the previous slide. But the y-intercept is very straightforward. You just let x be equal to 0, and then you solve for y. In the ax squared plus bx plus c form, your y-intercept is always going to be that c value, because when you plug in 0 for x, those first two terms will shoot to 0. Whereas x-intercept, you set this entire function equal to 0, and that's where your factoring skills will come into play, because you want to factor and figure out what are all of your possible values of x that make this function equal to 0. And then once you find them, you want to put both in coordinate form. So anytime you're looking at your y-intercept, your x is 0, and then whatever your y is, that's the y value of your coordinate, whereas your x-intercept, you have now your y is 0, and then whatever your x coordinate point is. Okay, there are times where you won't have an x-intercept, and that's usually when your discriminant, when we're talking about quadratic functions, is negative, which means your roots or your zeros in your function are imaginary, so they're not in the real number system. And we'll do some work with that later on, but right now, let's just focus on plugging them into our functions that are real and then going from there. Okay, example 4, we want to find the intercepts of this parabola, and we're given x squared minus 2x minus 8. I'm going to write y-intercept, and then I'm going to write x-intercept. And I always like to remind myself so I don't forget, y-intercept is when x equals 0. X-intercept is when y equals 0. It's always the opposite. Y-intercept is always the easier one because you plug in 0 wherever you see an x, and then you're always going to get that c value, which is -8. So in coordinate point form, we have 0, -8. And then we can go ahead and plot this on our graph, which is right over here. Our x-intercept has a few more steps. We write our function out and we set it equal to 0. And then we want to see if we can factor, and if we can't factor, we utilize our quadratic formula. In this case, we actually can factor. We can break this up into x minus 4 and then x plus 2. Then we set each parentheses equal to 0 so that we can solve for our values of x. And so we have x is equal to 4 and x equals -2 as our two possible roots, zeros, x-intercepts. These are all synonyms of one another. In coordinate form, we're looking at 4, 0 and -2, 0. And then we can go ahead and plot these. And we want to label, especially if they ask us to label. So 4, 0. Another x-intercept, which is -2, 0. And then we have our y-intercept, which is 0, -8. And so our answers are done. We were just asked to find our y-intercept and our x-intercepts. However, if we wanted to graph it just for extra practice, off to the side here, let's quickly find our axis of symmetry, our -b/2a, which ends up being +2/2, which is 1. And then we plug in that 1 into our function again to help us with computing our vertex. And so we end up getting, when x is equal to 1, we get our y is -9. So our vertex, our h, k, is 1, -9. And then let's go ahead and plot this on the graph. This says vertex. And then we can plot in our axis of symmetry too. And we know based off of our A value, our A is equal to 1, which is greater than 0, so it fans up. So axis of symmetry, x is equal to 1. Vertex 1, comma, -9. Always labeling your stuff so that you can get full credit for problems like these. If our y-intercept is 0, comma, -8, let's reflect over our axis of symmetry line, put in that 2, comma, -8 point, and then finally, let's connect some dots. Write out our function. We're looking at x squared minus 2x minus 8. And then we're done. So we have a page of notes on the next slide, and then we'll have another example that we'll do together. This slide is just talking about our discriminant. So just recall your quadratic formula, the whole x equals -b plus or minus square root b squared minus 4ac all over 2a. Remember, it goes to the melody of Pop Goes the Weasel. Well, we're really honing in on what's underneath that square root sign, which is known as our discriminant. When we have a negative underneath the square root, there's going to be no real solution because the square root of a negative number is imaginary. And this is where we won't have any x-intercepts. So an example visually would be a parabola or a quadratic function like this. Whereas, let's say underneath the square root sign, we had 0. The square root of 0 is 0, and then we're just looking at our x values that are just -b over 2a. However, any quadratic function will always have two solutions. And so this is just showing one. More specifically, it's the same solution with a multiplicity of 2. It's being repeated twice, aka it's bouncing off the x-axis. So visually, you'll see this sort of bounce off the x-axis, only hitting the x-axis once, but it's bouncing off to represent that multiplicity of 2. And then finally, if you're looking at a value that is greater than 0, whether it's a perfect square or whether it's just any random number, 12, for instance, you're going to get two distinct real solutions because then you have this plus or minus that you are applying to your quadratic formula, which means you'll have two different x-intercepts, just like we have indicated over here in our visual all the way to the left. Again, this is when our discriminant, when our value underneath that square root sign is a positive value. Two distinct solutions. So let's do another example together. We're asked to find these intercepts. And again, you don't have to graph it, but maybe we will graph it just for some extra practice. We have 5x squared plus x plus 4. Our x-intercept versus our y-intercepts. I'm writing the definitions again. Y-intercept when x equals 0, x-intercept when x equals 0, let's do y first because it's really just our constant, right? Everything else ends up shooting to 0. So in coordinate point form, we're just looking at 0, 4. If we plot this, there it is. Whereas for our x-intercept, we take our entire quadratic function and we set it equal to 0. So again, we want to see if we can factor here. And if we can't, we can utilize the quadratic formula. So first off, you notice that our a value is greater than 1. So let's utilize our AC method. The product of a and c is simply 20. And then our b is 1. What are factor pairs of 20 that add to 1? We have, C, 4 and 5. So 5 times -4 doesn't look like we can use our AC method. So let's jump into our quadratic formula. We have x is equal to -b, so -1 plus or minus square root b squared, which is 1 squared, minus 4 times a, which is 5, times c, which is 4, all over 2 times 5. And you can easily see that your discriminant is negative. So there actually aren't going to be any x-intercepts here. You have 1 minus 20 times 4, which is 80, over 10. And then we end up getting the square root of -79 over 10, which I'm actually not going to plot on the graph. But what we could do off to the side, so let's write no x-intercepts. Again, you're not asked to graph on this problem, so once you have these highlighted answers, you are done and you would receive full credit for this problem. But I'm just graphing to show you what our parabola is going to look like. So our axis of symmetry is -b over 2a, so -1 over 2 times 5, which is 10. And then if we plug this in, we can find our vertex. We're dealing with a bunch of fractional numbers here. Minus 1 over 10 plus 4. 4 is the same as 40 over 10. So we're looking at 1 over 100, which is really 5 over 100, minus 1 over 10 plus 40 over 10. 5 goes into 120 times, so this is really 1 over 20. And then 40 minus 1 is 39. 39 over 10 is the same as 78 over 20. So we're really just looking at 79 over 20, which is a little less than 4, right? It's 3 and 19/20. So our vertex is -1/10, comma, 3 and 19/20. Which is, say right here. And do that little reflection. So we're looking at a parabola, it's fanning upwards. It's going to be something like this. Okay. Let's move to the next slide. So this is just a note slide. We've done a lot of graphing quadratics, even though we didn't have to, just to sort of prepare you for these next examples where now we're asked to properly graph quadratic functions. And these are the steps to go about it, just like we have been doing. Identifying, is our parabola fanning upwards? Is it fanning downwards? Let's identify that axis of symmetry so that we can plug it into our function in order to figure out our coordinate of our vertex. Then let's identify both our x-intercepts and our y-intercepts. Y-intercept, x equals 0. X-intercept, 1y equals 0. And then finally, let's put all those 5 steps together in order to properly graph it on our coordinate plane. So now let's look at example 6, and we're going to graph this quadratic function together. First step, our a is equal to 1, our b equals 6, our c is equal to -9. Really honing in on that a value because it is greater than 0, which tells us that it fans upward. That's our first step. Second step, identify our axis of symmetry. Our axis of symmetry is when we're looking at -b over 2a. Our b value here is 6. -6 divided by 2 times 1 is just -3. All right. Third step, vertex. Our h comma k. Well, our h value is -3, but how do we figure out our k? We plug in -3 into our original function, and we solve for that y value, hence our k value. Wherever you see an x, you put in parentheses, and then you fill those parentheses with our -3. Let's simplify. -3 in parentheses squared is 9, times that negative on the outside gives you -9. 6 times -3 is -18. And then we have another -9. So we're looking at -18 minus 18, which gives us -36, which means our vertex is going to be way off our graph. Okay. Fourth step, let's identify both our x and y intercepts. So again, our x-intercept when our y equals 0, and then our y-intercept when x equals 0, aka just our constant, 0, -9, which we can easily plot, so I'm just going to put that in right now. And then our x-intercept, we take our function -x squared plus 6x minus 9 and set that equal to 0. I like not having a negative a value, so I'm actually going to move all of these to that right-hand side. Or you can just divide every term by -1. And so now we're looking at x squared minus 6x plus 9 is equal to 0. And then let's go ahead and factor that. So this can be factored into x minus 3 in parentheses x minus 3. Which tells us it's going to bounce off the x-axis. Our x is equal to 3 with a multiplicity of 2. Right? coordinate form, what does that look like? We have 3, 0. And then we're going to go ahead and plot in our axis of symmetry, which is at -3. Let's make this dotted. And then our vertex is all the way on the bottom, so this probably won't even justify where our vertex is, but I'll put it in there. I'll just say this is -36. And then we probably should go a little bit underneath the slide. That y-intercept here, we have, let's just make sure. Hey, we made a mistake. What was our mistake here? Our a value isn't +1, it's -1, which means this is fanning downwards. And then I put that in incorrectly into our axis of symmetry. Yeah, that makes a little bit more sense, right? Because -6 divided by -2 is a +3, which means we won't be looking at this large number. We plug in a +3. That's why it's always good to check your work. Then we have, once again, -9, but this is now a +18. So then this actually shoots to 0, right? Because it's -18 plus 18, which is just 0. So our vertex is, we're going to move this whole axis of symmetry here. Let's see if I can move it to 3. Actually, let me first erase this. Axis of symmetry is at x equals 3. +3. And then our vertex is at 3, 0. This is 0. Fanning downwards. So we don't need these points at the bottom here. Y-intercept is still the same, and so is our x-intercept. Our x-intercept actually also happens to be the vertex. But now we can add in that additional point from the reflection over our axis of symmetry. And there we go. Connect the dots, label your graph properly. So we have our y-intercept, which is 0, -9. And then we have our vertex and x-intercept, which is at 3, 0. And then we have our function. F of x is equal to -x² plus 6x minus 9. And we're done. It's always a good idea to check your work, especially when you have a really high y value. Check to make sure your calculations are all correct. But let's do another example together. All right, so now for our example 7, we have this quadratic function. we have our f of x is equal to x squared plus 4x plus 5. We go through the same process all over again. Let's first identify our a, b, and c values. 1, 4, and 5, and double check. You're not missing any negatives here. We're not. Our a is positive here, which means it's going to fan upwards actually this time. Whereas if you noticed on the previous slide, it was fanning downward. And then let's jump into identifying our axis of symmetry, our negative b over 2a, which is negative 4 over 2 times 1, which gives you negative 2. And let's plot that. So x is equal to negative 2. And now that we have our axis of symmetry, now we can plug this in to find our vertex. What is our function evaluated at negative 2? Wherever you see an x, put in some parentheses, and then inside those parentheses, fill them in with negative 2. So now we're looking at negative 2 squared, which is 4. 4 times negative 2 is negative 8, plus 5. So negative 4 plus 5, which gives you a positive 1, which means our vertex, our h comma k, is simply negative 2 comma 1. Let's go ahead and plot that over here. Again, it's going to be fanning upwards. Now let's identify our x and y intercepts. Y-intercept when x equals 0, aka it's just our constant. So 0 comma 5 that we can go ahead and plot. And then if we reflect over our axis of symmetry, another point is at negative 4 comma 5. And then our x-intercept, it's fanning upwards, which means our function is actually going to look something like this. We can label our function f of x equals x squared plus 4x plus 5. But you'll see that there's no x-intercept here, and we can test it using our quadratic formula. You'll notice that the discriminant, our b squared minus 4ac, is going to be negative, right? Our b is 4, so 4 squared minus 4 times 1 times 5 gives us 16 minus 20, which is negative 4, which is less than 0. So we have no x-intercepts. And that's it. We graphed our quadratic function, and we're done. I believe this example 8 is actually the same, x squared plus 4x plus 5. So it's just a repeated question. So I'm just going to put an X, say, and write repeated example. Or in parentheses, same as example 7. And then our last part in this section is being able to solve for our maximum and minimums in our quadratic function, which is really the combination of identifying, is our a value positive or negative? Is it fanning upwards or is it fanning downwards? And then really honing in on that vertex point, because if our a is positive and it's fanning upwards, we're going to have a minimum at that bottom point. At specifically, we really like to emphasize at that y value because that gives us that absolute minimum. Whereas if our a is negative, then our parabola is now upside down, and we're going to have a maximum at that vertex, again, specifically at that y coordinate, which is that k value. So now knowing all of this, let's apply it to this example. We're just asked to find the minimum or the maximum of this quadratic. So we look at our A is equal to 1 here. 1 is positive, so it's greater than 0, which means it's going to fan, or it fans upwards. If it fans upwards, what are we looking at? We're looking at a minimum value. So now let's utilize our axis of symmetry in order to identify the vertex and distinguish what that minimum value is. Negative b over 2a. Our b is 2 and our c we don't need here, but I'll put in. It's always good to practice. So we have negative 2 over 2 times 1, which is just negative 1. Plug this back into our original function. Wherever you see an x, draw some parentheses, and then fill those parentheses with negative 1. And so we're looking at negative 1 in parentheses squared is 1. 2 times negative 1 is negative 2. So our vertex is simply at negative 1, comma, negative 9. Negative 1, comma, negative 9. Let's plot that. We wanted to go ahead and plot our vertical line for our axis of symmetry. We can go ahead and do that too. Again, you're really not asked to graph this one, but I want to be able to show you guys visually what this looks like. Our y-intercept, 0, comma, negative 8. Do that reflection, and we have negative 2, comma, negative 8. And then if we now connect the dots, because again, we're just sketching here to just visually see what's going on. We're looking at the following. So, again, don't forget to write your quadratic formula here. But then what are we able to determine? We're able to determine that we have a minimum at that vertex, negative 1, negative 9, but more specifically, we really want to hone in on that k value. So you write it as, therefore, we have a minimum value at y is equal to negative 9. And that completes the problem. And we're done. So, what I would love for you guys to do is take a look at these workbook exercises, these extra problems. And this will be really good practice for you having a very good understanding of uh, identifying your A values, fanning upwards, fanning downwards, knowing how to calculate your axis of symmetry, how it folds, the parabola folds on top of itself so that you can identify that vertex. And then identifying your x and y intercepts so that you can properly graph your quadratic function, and then bringing everything all together to actually put it on a coordinate plane. I hope this was helpful. Please let me know if you have any questions, and good luck with the workbook exercise problems. Take care.